welcome to the lectures for Class 3. In this set of lectures, we are going to finish up Russell and Norvig Chapter 7, and we'll start taking a look at the prologue book, Chapters 1 and 2. So we've been looking at propositional logic and trying to evaluate the semantics of propositional logic. And in our lecture and in class, we've been looking at truth tables, and here's an example of the kind of thing we're talking about. So for instance, if P is false and Q is true, then we can conclude that P implies Q. All right, so let's try applying these kinds of ideas in the context of the Wumpus world. So here's some things we can represent. For instance, let's say that P of ij, which stands for pit, is true if there's a pit in ij. And let's let B of ij be true if there's a breeze in square I and j. Things we can say, for instance, might be that there is no pit in square 1, 1. That's true, in fact, in the example we've got. Or there is no breeze in square 1, 1. That's true. But there is a breeze in 2, 1, so B of 2, 1 is true, along with not P of 1, 1 and not B of 2, 1. So if it's true that pits cause breezes in adjacent squares, can we use this kind of representation to say that for these examples? And of course we can. So if there's a breeze in 1, 1, then it must be true that there's either a pit in 1, 2 or there's a pit in 2, 1. And of course this is a logical or, so both of them could be true. And like conversely, because this implication runs both ways, if there's a pit in 1, 2 or a pit in 2, 1, you'll feel a breeze in 1, 1. Similarly, for square 2, 1, which is adjacent to 3 other squares, that's equivalent to saying that there's a pit in 1, 1, or there's a pit in 2, 2, or there's a pit in 3, 1. And conversely, if there's a pit in any of those, then you'll feel a breeze in 2, 1. So that's how the representation works. And in fact, this mutual implication means that a square is breezy if and only if there's an adjacent pit. Let's turn now to a couple of concepts that we're going to find useful. The first is the concept of validity. So remember, in propositional logic, a proposition can have the value of either true or false. So some proposition A could be true or it could be false. And those are the two models for proposition A. So a sentence is valid if it's true in all models. So true is true in all models. A or not A is true in all models. A implies A, it's a tautology, but it's true in all models. And a rule of logic like A and A implies B is true in all models. That method of reasoning is true in all models. The other concept we need is satisfiability. So a sentence is satisfiable if it's true in some model, that is, any model. So given that A and B can each take the values of true and false, it's true. A sentence like A or B is satisfiable because A could take on the value true or B could take on the value true or both. And similarly, some other proposition like C is satisfiable because it could take on the value true. On the other hand, a sentence is unsatisfiable if there is no model in which it's true. So for instance, a sentence like A and not A is never true and thus unsatisfiable. Now we're going to turn to horn clauses, and these turn out to be very important for a couple of reasons. First, sort of practically speaking, horn clauses are the representation used in prologue. And second, and basically it's the reason prologue uses this representation, it turns out to be a very efficient representation for reasoning. So a knowledge base that uses horn clauses is a conjunction of horn clauses. What's a horn clause? Well, it's either a proposition symbol, that is a fact that we know, or it's an implication where on the left-hand side there's a conjunction of symbols, in other words, A and B and C and so forth. And on the right-hand side, the thing that's being implied is a single symbol. So it's either a single symbol or it's a conjunction of symbols that implies a single symbol. So for instance, a knowledge base that's a conjunction of horn clauses might be the symbol C, which is a single proposition symbol, and B implies A, and C and D implies B. Now, it turns out that modus ponens, the form of reasoning, is complete for horn knowledge bases. In other words, if it's true, we can derive it using modus ponens. So if you have a set of propositions or sentences, let's say alpha 1 through alpha n, and you know that alpha 1 and alpha 2 and alpha through alpha n implies beta, then we're going to be able to conclude beta. Now, this form of reasoning with horn clauses can be used in what's called forward chaining or backward chaining. And it turns out that these algorithms are very straightforward and run in linear time. Prolog uses backward chaining, but we'll take a look at both forward and backward chaining so we can understand what that means. Under forward chaining, the idea is that we start with what we know and we keep deriving the implications of what we know until eventually we derive the thing we're looking for. So let's say that we have the following knowledge base of horn clauses. P implies Q, L and M implies P, B and L imply M, A and P implies L, A and B implies L, and we also know A and B. And we can represent these propositions and relationships on the map at the right-hand side here. And so, for instance, we see here that this means that A and B implies L. So let's try running forward chaining with that. The algorithm in the book uses a counting mechanism for each implication so that you don't fire the same implication more than once. And that's what the red numbers mean here. We'll start by taking a look at the implications of A. So we've decremented the conjunctions that involve A, and because we have one side of it now taken care of. Now, we know A, and we've sort of exhausted the possibilities for A, but we also know B. So if we apply A and B, we conclude L, because we know that A and B implies L. Likewise, we know that B and L imply M, and we've checked both sides of that. What else can we deduce? Well, we also know that L and M implies P, okay? And what's more, P implies L, but we knew that already, so that doesn't really help us. But it's also true that P implies Q, which is, in fact, what we were aiming to find. So, having run all these implications forward, we eventually arrive at Q. So that's forward chaining. It's sort of called like blind search because you keep firing the implications, adding new things to the knowledge base until you find out, until you reach something that it is what you're looking for. Backward chaining, as you might imagine for the name, instead of going forward, it goes backwards. In other words, we'll have some query Q, and to prove it by backward chaining, we'll see if we already know Q, or if it's not already known, we'll check the premises of some rule that concludes Q. Now, if there is no horn clause in our database which has its as its implication Q, then we're not going to be able to prove it. But assuming there is some rule with Q on the right-hand side, we'll check the premises and recursively see if those premises are true. Now, we want to avoid loops, so every time we add a sub-goal, we'll check if the new sub-goal is already on our stack so we don't try to prove the same thing more than once. So to avoid repeated work, we'll check to see if a new sub-goal has either already been proved true or has already failed. There's no point in proving anything more than once. Okay, so here the thing we want to prove is in green, and the things we know, as we had in the forward chaining case, are in red. So we know A and B, and we're trying to prove Q. Okay, so what implies Q? Well, the only rule we have that implies Q is that P implies Q. So what we'll do is check to see if P is true. So if P is true, then Q will be true. Now, what implies P? Well, there's one rule that implies P. That rule is L and M. So what we'll do is check to see if L and M are true. All right. Now, what are the antecedents of those? Well, we know that L is true if A and B is true, and what's more, P implies L, so that's true. We've got these extra elements in the goal stack, we can take them off. But now we know that L is true because A and B are true. We tried to prove it, and we did succeed in proving it. Now remember that what we're trying to prove now is we still have M left on our as an open query. So, but luckily enough, we happen to know that L and B are true. So that means that when we check L and B, M is going to be true. And now, because L and M is true, and the query we have in our stack is whether P is true, P is going to be true, and the last remaining query on our stack is going to be P implies Q, and sure enough, that's true. So if we're comparing forward versus backward chaining, as I said, forward chaining is data-driven. It's a kind of automatic or unconscious processing. You start with what you've got, and you try to figure out what you go from there. So it's good for things like object recognition or routine decisions. But on the other hand, if there are a lot of horn clauses with implications in them, we might do a lot of work that's irrelevant to what it is that's our goal. Conversely, backward chaining is goal-driven, and it's really appropriate for problem solving. Appropriate for me, where are my keys? Appropriate maybe for you, how do I get into a PhD program? And it turns out that the complexity of backward chaining can be much less than linear in the size of the knowledge base. It's quite efficient, and you'll see it in action in Prolog. So what do we know about logical agents? Well, we know that logical agents apply inference to a knowledge base to derive new information and make decisions. We looked at some basic concepts of logic. The syntax, that is the formal structure of the sentences, what constitutes a syntactically valid sentence. We looked at the semantics of sentences, that is their truth with respect to models, and we worked on defining and checking models. We looked at entailment, that is the necessary truth of one sentence given another. We looked at inference, that is ways of deriving sentences from other sentences. We explored the idea of soundness, that is our inference method is sound if what we can derive through the inference method produces only sentences that are entailed by the knowledge base. And we also looked at the idea of completeness, that is an inference method is complete if the inference method can derive all the sentences entailed by the knowledge base. We explored Wumpus world, which turns out to require the ability to represent partial and negated information, reasoning by cases, and so forth. And we looked at forward and backward chaining, which are both linear time algorithm, and it turns out that they're complete if we use horn clauses. That is, we can derive everything that's true entailed by the knowledge base. So that's what I want you to know about Chapter 7, and I'll see you in class.